Now let us see error detection and correction. Now error correction can be handled in two ways. If the error is discovered, what receiver can do is, receiver can ask the sender to retransmit the entire data unit. This is one option. So the other option is the receiver can use an error correcting code which automatically corrects certain errors. We'll see one of them. If it is a single bit error correction, then we'll use a parity bit, and the secret of this error correction is to locate the invalid bit or bits. That bit which was accidentally or by some means has received in not in order, means the wrong bit has been received. So for ASCII code, it needs a 3-bit redundancy code, right? Because I'll show you how this redundancy bit is how it is computed to calculate the number of redundancy bit R, which is required to correct a given data of bit M. These are the M bits and these are the redundancy bits. So M, R, these are the total M plus R. So what we are going to send from the sender is M plus R bits. How it is computed? If the total number of bits in a transmittable unit is M plus R, see, this is just we have seen, then the R must be able to indicate at least M plus R plus 1 different states. This is the expression which is indicating what we have just learned. Now 2 to the power should always be greater than or equal to M plus R plus 1. Let us take an example. For our ASCII, the smallest value of R that can satisfy this equation is what? 4. 3 cannot satisfy. You place 4 here, you will get this as 2 to the power 4, that is your 16, and this is equal to 7 plus 4 is 11 plus 12. So 16 is greater than or equal to this number, so this is going to work. Now the relationship you should learn, because this is already being followed by this particular expression. Number of data bits, if it is 1, the redundancy bit you have to use is 2, for 2, 3, for 3, 3, and for 7, as we have just seen, it has to be 4. So in all you have to send 11 in totality. So we'll see Hamming code. This was developed by R.W. Hamming. What we do is that if this is our data, we have data bits of 1, 2, 3, 4, 5, 6, 7. So our ASCII or 7-bit is our data. How many bits do we need to have redundancy? Or Hamming says that you should have at least 4 of them. You remember that expression? That expression says that you have to have 4 redundancy bits, and which place these Hamming bits are, or the parity bits are going to take. This is 2 to the power 0, only 2 to the power n places. This is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, and this is 2 to the power 3. So all these red R's are the position of your redundant bits. The other position is taken by the data. I'll show you with an example. This R1, this you have to learn. This is being given by Hamming. So you have to learn this, that the R1 bit, this is each R bit is the VRC bit of for one combination of data bits. So R1 has the combination of 1, 3, 5, 7, 9, 11. R2 has the combination of 2, 3, 6, 7, 10, 11. R4 is for 4, 5, 6, 7. R8 is for 8, 9, 10, 11. Now, what I wrote here and I told you, I'll show it with an example or with a diagram first. This R1 is going to take care of what? 1, 3, 5, 7, 9, 11. So R1 will be taking care of 3, 5, 7, 9, 11. R2 will take care of whose bits, or where are they lying? They are lying at 3, 6, 7, 10 and 11 position. Again, this R4 will take care of 5, 6, 7, and this R8 will take care of 9, 10, 11 and its own position. So let's see that this is the data. This is the data which we want to send. These are the position which I have marked. No data is here because we are going to put the R bit or the parity bit or the redundant bit here. This is our data. So let us write these data here. place the data at its position 1 0 0, this 1 0 0 and 1 1 0 1. We cannot place it here because these places are actually reserved for the redundant or parity bit or the Hamming bits. Now this first position, as I said, this it is going to take care of 3 5 7 9 11. So 3 5, this 3 5 7 9 and 11. What are the number of ones in this particular combination? This is 1, this is 0, this is 1, this is 1. So how many ones are there? There are only 3 ones. So to make a even parity, you have to place 1 here. Okay, this place was initially empty. Now we placed a 1 here just to make the combination of 11 9 7 5 3 and this as 1. In the similar fashion, for R2 is responsible for 11 10 7 6 and 3. So let us see the position. We have not placed anything here, but we'll see the position or the bits here. 3. How many ones are there? 1 and 2 and 3 and 4. There are 4 ones in 3, 6, 7, 10th and 11th position. So we don't have to add any one bit because they are already showing even parity. So we'll place 0 here. This is how we got the 0 here. Now coming to R4 as you know that R4 takes care of 5, 6, 7. So we'll go to 5, 6, 7 and we see how many numbers of 1 are there. How many number of 1 are there? 2 1. So this 1 and 2, the 2 1. So we don't have to place any 1 here. We can just place a 0 to make it a even parity. In the same fashion, again for R8 is taking care of 9, 10, 11. So we'll go to a 9, 10, 11 position. There is only 1. So we have to, or we are forced to place a 1 to make it a even parity. Now all our positions are filled. These positions are filled by the data, and these gray positions, these are placed by the numbers or the bits we have found just to make them the other ones even parity. Now what happens that this was our data and it was sent and there was an error. There was an error in this particular bit. 1 has become 0. Now how? By using Hamming we can get it first found and then corrected. Detected and corrected. So what we'll do, we'll see this first R1 position. It is combination of 1, 3, 5, 7, 9, 11, as you might have remembered by now. How many ones are there? 1, 2 and 3. 3 ones are there. So because it is not an even parity, you have to place a 1 here. So we place a 1 here. Now coming to this, the other combination for R2, we see how many ones are there. 1, 2, 3. So again we have to place a 1 here. Right? Now for this R3, how many ones are there? We have only 1. So we have again you have to place a 1 here. In the final combination, how many ones are there? 1. There are 2 ones, so no problem. We don't have to place any 1 here. We have to place a 0. Now what we have got, 1 1 1 0. You take the binary number of this. This is 7, and now this is the 7 bit which you have to change or which you have to correct. So this is the beauty of your Hamming code. It detects an error and it corrects it also. There are multiple bit error correction also. Redundancy bits calculated on overlapping sets of data units can also be used to correct the multiple bit error. That means to correct double bit errors, we must take into consideration that 2 bits can be combination of any 2 bits in the entire sequence. So hope you got the idea of error correction. Thank you so much. Take care of yourself.